substitute, what do I know about z of n? This is x1 of n plus x2 of n. This is minus 2 x1 of n minus 1 minus 2 x2 of n minus 1. And now I can recombine those things and say, hey, actually what I did get was the sum of the outputs. Right? And I say, okay, this is in fact the sum of the outputs. And so now I have verified that this is correct. Okay. And the same way, I could say, okay, now instead, let me consider this guy. And now what I can do is put that in the system. So when I put Cn through the system, I get A Cn, which is equal to A x1n minus 2 x1 n minus 1. And I can see, yes, that is exactly what I got, right? And so, then I can say homogeneity is confirmed. That's a little bit of a pain to have to do these two steps for every time I want to do this. And so let's do it all at once, right? So an easier way to do it all at once is to say, okay, let's suppose that we have two constants, right? So all at once, let's say I have z is equal to a x1 of n plus b x2 of n. I put that through the system. What I get is z of n. No, I feel like that's something wrong with the previous stage. Oh, yeah. Oh, I know. No, this is why I wrong. Sorry, forget I said that. So go back to this. What comes through the system is this, right? I get z of n minus 2 z of n minus 1. Then I plug in what I know. This is a x1 of n minus 2 a of x1 of n minus 1. And then I resort. This is the a times this, and this is a times 1. Right? Sorry about that. I knew I did something wrong. So let me do this right for this. So what I get is z of n minus 2z of n minus 1. And I associate, what do I know about z? Well, this is equal to a x1 of n plus b x2 of n minus 2 a x1 of n minus 1 plus b x2 of n minus 1. You can see where this is going. And now I can resort this stuff. And then I can see this is in fact the linear combination that I expected. And so when you do the homework and when you prove things are linear, it's usually easier to do it this way. It is true that some systems can have the additive property but not the homogeneous property, and vice versa. So it's not like one necessarily applies to the other. In theory, you have to take both, or you have to do it this way. Okay. Okay. And so in terms of how would you guess whether a system is linear, well, usually the linear system is made up of basically, instances of the signal that pop out like previous signal values. Okay. But it takes a little practice to be able to tell, okay, can I inspect this visually and tell whether it's linear or not? So let's take a look at this signal. Okay. So it's not linear. Who was linear? You people, who was not linear? You people? So 50 extensions, okay. So basically, we have to check, right? So I mean, instead of guessing, you have to figure it out. So let's suppose that I have x1 goes in the system. What comes out is 3x1 n plus 5. I put x2 in the system. What comes out is this. Now let's suppose I put c, which is equal to, let's just put the sum of these things in the system. I'm just going to check activity. Well, to put that in the system, what I get is 3 c of n plus 5. I plug in what I know about c, which is the sum of these two things, plus 5. And now I ask myself, is this equal here to this plus that? And the answer is no, right? Because if I add these two things together, I get the 3 times the sum plus 10. Here I only have the plus 5, right? So, not linear. Okay. And so, if you're trying to show, or if you suspect that something is not linear, you can just prove it with a counterexample, right? You give me one signal or a pair of signals for which one of these properties fails, right? If it fails for one, that's all you have to do, right? And so the easiest way to prove that something is not linear usually involves simple functions like constants or delta functions, right? So in this case, let's suppose that, counterexample. Let's suppose that my x1 of n is just equal to 1 for all time. And let's suppose that x2 of n is equal to 2 for all time. Okay? That means that if I put in 1 into the system, what I get is 3 times 1 plus 5 is 8. If I put in 2 into the system, I get 3 times 2 is 6 plus 5 is 11, right? And so here I can immediately conclude the system is not linear, right? Because since 2 is twice 1, this should be twice 8, and it's not. So if the system was linear, I expect 16, so I got 11, right? And so this is all you have to say, or I guess the way to say it like this. This is all you have to say to tell me the system is not linear, okay? So when you're not sure, try some very simple functions, right? Don't try anything too crazy. Constants, delta functions, those are the best. Okay, so questions or comments about linearity? So another useful property, just as a side note, is that since I'm an expert, I can tell this immediately it wasn't linear. One thing that has to be true for a linear system is that, remember that homogeneity is part of the linearity statement, right? So homogeneity says that if I multiply this by something, what I have to get out is the same multiple of the output, right? And since this has to be true for any constant, I could choose 0, right? So if I put 0 in here, that means that the linear system must have, if 0 goes in, that if a equals 0, 0 has to come out, right? And we can see that wasn't true for the system over here, right? Put 0 in and get 5 out, so that's B equals 1. Does A need to be real? I think that for our purposes, we're always going to be talking about real coefficients. I think that if you're talking about general linearity, then A could be any number you want in complex number, right? And in fact, the realness of the coefficient will never come into play when you're doing your proofs, so it doesn't really matter. Other comments or questions? Okay. So another property that's really important is called time invariance, okay? And so this means that the system behaves the same way regardless of when I apply the input. Okay? So the kind of intuition is that the system behaves the same way regardless of what input is applied. And so mathematically what that means is that if I put a signal into the system and I compare it to what I get if I delay the signal by some number of units, what I should get out is the same output delayed by some number of units, right? And so, again, the intuition is that many real-world systems should be time invariant, right? So if I decide to bake some toast at 3 p.m., I put the toaster in, the toast comes out 3:05 p.m., it shouldn't be any different if I go and put my toast in at midnight and it comes out 12:05, right? So the time that I do something shouldn't depend, shouldn't affect the system, right? But again, if you think of many systems that are not time invariant, right? So for example, think about the speed it takes you to download something at 3 p.m. versus the speed it takes you at midnight, right? So fairly internet traffic is highly, non-time invariant, right? And so there are lots of, and again, just in the same way that we try to find the closest linear system, sometimes we try and, wangle a system into being time invariant, but sometimes it's a lot harder, right? Because, lots of real-world systems are not time invariant. So we think a model what the system is doing as a function of time. Okay. And so again, we have to prove or disprove this is true for given systems. And so this, I always find that people have a little more of a hard time with this. I want to do a couple of careful examples to show how that works. Okay. So let's take our same system that we had before. So this is the system from before. We have x of n minus 2, x of n minus 1. The question is it time invariant? So what we need to do is, again, we make a dummy signal. So let me call my signal C. And this time, the dummy signal is going to be a shifted version of the input. Okay. And now, I guess I should have done this all on one page. Let me see if I can do this a little better. So now what happens if I put C into the system? Well, what comes out is C of n minus 2 C of n minus 1. Okay. And now I plug in, what do I know for Z? I know that Z is equal to x of n minus n0. And here, again, I plug in what is Z of n minus 1. Just to be really pedantic, I'm going to say you always just kind of follow. I plug in n minus 1 into here, and n minus 1 into here. So I get n minus 1 minus n0. And I ask myself, is this equal to the output shifted by n0? And what would that be? Well, that would be, again, if I follow this up here, as I say, I plug in n minus n0 into here. So I have that equals x of n minus n0 minus 2 x of n minus n0 minus 1. And I can say that, hey, since this subtraction order doesn't matter, I can compare these two things and say, yes, I got the correctly shifted output that I was expecting. Okay. And so the common mistake is to always seem to come up with the fact that every system is time invariant, right? So let me show you an example of a system that's not time invariant and how you would, kind of come against it. So what about this system? Okay. So same kind of deal. What I'm going to do is I'm going to say, let's C equal a shifted version of the input. Okay. Now, when C of n goes into the system, what comes out is C of n squared. Right? Because when x goes into the system, what comes out is x of n squared. So now here, what is this? So C of n squared, I have to plug in n squared whenever I see an n here. So I get x of n squared minus n0. And now I ask myself, is this equal to the shifted version of the output? And for that, I have to plug in this wherever I see the n here. And so what I get here is x of n minus n0 squared, which is not the same as what I came up with when I put C through the system, right? So this is a non-time invariant system. So until you try and do this yourself, I think that it's kind of hard to see the difference. But after you work a couple examples, you can see the virtue of this approach, right? If you do it this way, you will never get a time invariant question wrong, where you just kind of plod through, okay, I need to make this separate signal, see what happens to that signal, substitute what I know, and compare it to the shifted output, right? Part of the issue is that, you're comparing two signals, right? You're comparing the shifted version of the output to what happens to the response of the system to the shifted input. And until you verify that those two things are the same, you can't assume anything about the system. You don't know exactly what the system may be doing to the signal. Okay? Again, in the same way that all you need to do to prove that something is not linear is to find a counterexample, the same thing is true for time invariance. You may need to use a different signal to be able to get at the counterexample, but still, things like double functions are generally a good way to start. So, counterexamples to time invariance, try double functions. So let's take our system again, right? So what we got here was y of n is x of n squared. Okay. And so let's think about what happens when we put a double function in the system, right? So what is the response to this function here, double function? Which, just to remind you from last time, is something that is 1 in the middle and 0 everywhere else. Okay. Well, what should we get? That's like saying that, if I just kind of plug in, that's like saying that y of 0 is x of 0. Y of 1 and y of negative 1 are both equal to x of 1. Y of 2 and y of negative 2 are both equal to x of 2, and so on. And I can see pretty fast that if I put the delta function in, that y of 0 is x of 0, that's going to be this. All the other values are, again, going to be 0. Right? So this is the response of the system to the delta function. Now, what is the response to the shifted version of the delta function, right? So let's suppose that I have a delta function that is shifted by 1 unit to the left. Okay. Well, that would be a signal that would look like this. Again, what would I get if I put that through the system? Well, I would apply the same system rule. I would say, okay, well, y0 is whatever x0 was. y1 and y minus 1 are both whatever this number is. So I'm going to get zeros here. So I'm only looking at positive values of the signal, right? Since there are positive values of this shifted signal, I get 0 across the board, right? And in this case, I would say, I shifted the output left by 1 unit. The output did not shift left by 1 unit like I expected it would, right? So again, this would be sufficient to prove that things were not time varying. And so, just again, to be kind of clear on terminology, right? So, we're going to talk, maybe it's a little bit today, but we're going to talk about next time a lot this concept of the impulse response, right? Which means that when I put the delta function in the system, I see what I get at, right? Now, technically, I can only really talk about the impulse response, but the impulse response is only really a useful quantity if the system is linear and time invariant, right? So here's an example where, yes, I can compute the response of the system to an impulse, but knowing this so-called impulse response doesn't mean the same thing as we usually do when we talk about LTI systems, because I can't talk about how the system responds to any other signal in terms of the impulse response, right? I can't get to this output knowing that this is the response to the impulse, right? So be careful talking about the impulse response until you're sure that the system is linear and time invariant to begin with. Okay, so I guess I kind of skip forward. So let me just ask questions. So, questions about time invariance. Okay, so again, if you took signals, you probably do these kinds of things with continuous time systems, and so the same idea applies to discrete time systems. And so on homework, I ask you to prove or disprove linearity and time invariance for a certain system or two, and you have to figure out how it works. Okay, and so kind of putting it all together, the thing that we care about the most in this class is linear time invariant systems. And these are often called LTI systems. Okay. And so from now on, or at least for the until I tell you so, we're going to assume that the systems we care about are all linear and time invariant. Okay. The reason for that is that it allows us to analyze how the system works in an extremely elegant and powerful way, right? Which corresponds to the impulse response, frequency response, C transform, all that kind of stuff is not possible if the system is not linear and time invariant. And so let's just say that real world systems are often modeled as LTI. Okay. And the reason is that, let's just say often a good approximation. There are lots of, systems that are almost linear, and that linearity is kind of good enough. Analysis is very easy, powerful. Right, those are the main reasons. And so you would take a whole, and that's not to say you can't analyze non-LTI systems, right? So for example, if you go further up our course curriculum into the 4,000 and 6,000 level, there are courses on this is a course called nonlinear control. What that means is how do you design control systems for nonlinear systems, right? So it's not like you have to just throw everything away if you don't have a linear system. But, when you guys are first starting out, we're not going to get too deeply into nonlinear systems. And so, the key idea is that, LTI systems kind of tie together all the stuff we talked about so far. This idea of delta function, differential equations, superposition, all this stuff comes together in this nice way. So the key concept is what's called superposition. Okay. And what do I mean by that? Well, kind of what I mean is that, just kind of preview how it works. So, if I were to take a combination of, let's say I take some signal, x, and I represent it, I take a bunch of shifted versions of that signal. I guess if I was smart, I would have labeled these like this. So numbers match up. Plus dot dot dot. If I put that into an LTI system, there's not. Well, what should come out of that LTI system is corresponding sums of signals like this. Right? that's like saying that, well, from the linearity part, it's like saying that I can take apart each of these sums and coefficients separately, right? So I know that I can kind of go from here to here, from here to here, from here to here. Time invariance tells me that the shifted version of this x is going to be the shifted version of this y. It's not like this possibly could produce some other weird, output signal, right? So basically I'm writing the output of this LTI system entirely in terms of knowing what happens to just the original signal, okay? And so this is really important because what we care the most about is the delta function, okay? So, consider an arbitrary signal where we have, whatever these values look like here. And I want to know, what does this signal come out as after I put it through an LTI system, right? And so what I can think of is this signal is like, let me just write, some numbers here that tell me how tall each of these sticks is. So I can think about this as saying, well, this looks like this simple signal here plus this simple signal here, where everything else is 0, plus this simple signal here, and so on. Right? And I can furthermore kind of decompose this by saying, well, that looks like, this very simple signal here multiplied by A0 plus this same very simple signal shifted over multiplied by whatever A1 is plus this same guy shifted over times A2 and so on, right? Which is like saying I have A0 times the delta function plus A1 times the delta function delayed by 1 unit plus A2 times the delta function delayed by 2 units. That's a crappy and so on, right? So what I've done is I've taken my original signal x and I've taken it apart into pieces that involve the delta function, right? And to say this in a more mathematical way, sorry, I guess I cut off the right hand side. To say this more mathematically, that's like saying that my x of n is the sum of the values of x multiplied by corresponding shifted versions of the delta function. Okay, so again, that looks kind of scary, maybe, but if you think about it, this delta function, right, is only, this delta function fires, basically, at n equals k. And when it fires, what is its value? It's whatever that x of k is, right? And so again, we actually already introduced this in the last lecture, right? This is sometimes called the sifting property of delta functions. Right? Because kind of one way to think about this is that here I have infinitely many functions added together, but basically only one of these functions is not 0, right? Because I plug in, n here, that's like saying, well, the only place where this delta is a function of k, the only place where this thing is not 0 is when k equals n, right? And when k equals n, I get x of n, so this is kind of like almost like a syllogism. Okay? So why is it exciting? Well, it's exciting because it means that we can ask ourselves what happens when we put this signal through the system, right? So first of all, let's suppose we have an LTI system. Right? And now I'm assuming that. That's very important, right? So I put the impulse function in. And let's call the output of that h of n, right? So this is the unit impulse, also known as delta function. Right, I put that in the system, and we're going to call what comes out the impulse response. Okay? And we always use little h of n as the response to the delta function. Okay? So now the super exciting thing is that I can figure out what is the response of the system to any input x by looking at only knowing what the system did to the impulse. Okay, and so let's plug this into here using my properties of linearity and time invariance. So what is the response to xn? Well, I'm going to say my response of the system to xn is going to be writing it like this large sum. And now I can say, okay, well, for the purposes of this discussion, right, k is just, x, k, they're just numbers, right? They're just numbers. They're multiplying the height of the delta functions, right? So they're going to play the role of constants for the purposes of understanding how the system is processing these sum of delta functions. And so from linearity says that I can immediately take these constants out of the sum and also, look at the sum of the responses like this. I can basically immediately say that my output is like these constants times whatever the system does to this set of signals. And by time invariance, I can say, well, that response of the system to the shifted delta function is going to be the shifted version of the impulse response, right? So if k was equal to 0, I would just have a regular impulse response. If k was equal to 1, it would be like the impulse response delayed by 1, right? And so